Okay, today we want to focus on how many solutions a matrix vector equation or a system of equation has. So before we get started with a full system, let's just look at a standard system, a standard equation with one variable. So we have a nice example right here. And this might be an example that's quite easy to solve. Right? We can just FOIL this guy out on the right. And we'll end up with 5x plus 10 equals 5x plus 10. And we get 5x equals 5x, and we get 0 equals 0. So this is a strong indicator, when we have 0 equals 0, that any x works. Or more explicitly, we have infinitely many solutions. This equation is true no matter what x you pick. There is no meaningful solution. Any x will work. On the flip side, we can adjust this equation and give a slightly different example. So we start off with 5x plus 10 equals 5 times x plus 1 and try to simplify this. We'll end up with 5x plus 10 equals 5x plus 5. Or when we simplify this, we'll end up with 10 equals 5. Or if you want to simplify it even further, we'll get 5 equals 0. And this right here, this is bogus. So what this strongly indicates is that if you pick any x, no matter how hard of an x that you pick, you're in fact never going to have something that satisfies the solution. In other words, this is no solution. And in the case of one variable, this is very easy to recognize. Either you can end up with 0 over 0 equals 0, or you'll end up with something non-zero equals 0. And it's very easy to distinguish which one is which and what case you're in. Albeit these cases are rare, when we go up to systems of equations or in higher dimensions, things like this are more common. So let's do an example. Let's focus on this example right here. Let's do x minus y equals 0 and minus x plus 2y equals 0. Right, so one thing I want to emphasize again is when you look at a system of equations like this, we can translate this into a matrix equation. So this matrix equation says we can take this matrix, which is just the coefficients of the given entries. So we're just taking the coefficients of the given entries and multiplying them by a vector xy, and this equals 0, 0. So let's just take a step back and appreciate what this is actually saying. Right? This equation asks a question. It asks the question, what vector xy, after applying this matrix, gives 0, 0. So in much the same way, you can go kind of up here and ask, okay, what number when multiplied by 5 and add 10 gives you the same thing as when you take what number, that same number plus 2 times 5. You can ask a question for each of these equations. You can ask an equation for this matrix vector equation. So before we dive into actually solving this, I just want to take a minute. Let's draw a geometric before and after picture. So we're going to take a before and after picture. So we can take certain vectors. You can just pick which ones you want. I'm just going to pick these for now. Let's do one more for giggles. We'll take each of those. And if we apply each of these separately, what will we end up with? So 1, 0, we're going to multiply that by our matrix. And we should end up with 1 minus 2 rather. 1 minus 2. And then likewise, the green vector 1, 0 is going to go to minus 1, 2. If we take 0.7, 0.7 and we apply it, what happens there? We'll actually end up with 0. And likewise, if we apply minus 0.7, minus 0.7, we'll end up with 0. The point of doing this is I just want you to see what this transformation is actually doing. So the blue vector goes there, and the pink vector, this is minus 0.7, 0.7. What will we end up with? We'll end up with minus 1.4 and 2.1. So minus 1.4 and 2.1, you'll end up with something over here. And you'll see in this case, what's happening is everything on this circle, everything on the edge of this circle here is getting smushed down to a line. So if we want to ask the question, okay, what points end up right here at 0, 0? That's our goal. Well, what points are those? The points that end up there, we can see are all the points that lie on this line right here. So all the points that lie on that line end up there. And geometrically, it's very clear that this system of equations, characterized by this matrix vector equation, has infinitely many solutions because I can squash anything on this line right here, and it will go down to 0, 0. Let's make a slight change of this. What happens if I ask the question, I'm going to change this equation very slightly. And we're going to change this equation, and we're going to change it just so that one of them has a 1. One of the zeros is a 1. So we're going to ask the question, what vector after translating by this matrix gives us 0, 1? So we can go back to this picture over here. We can go back to this picture. And now instead of this point right here in the center, we're going to ask for when does it hit 1, 0? When do you hit that point? What are all the before points that get there? But of course, we know that this is in fact impossible because this transformation is squishing all the points onto this line, that since this endpoint is not on the line, there's nothing that's going to end up being there. So geometrically, we can have an idea of what it looks like when things are either have no solution or have infinitely many solutions. But what does it mean algebraically? So let's do each of these examples separately. So let's go back here. We're going to take this guy. And we're going to do some row operations on this. So let's create an augmented matrix. We're just going to kind of get rid of this part right here. We're just going to turn that into a horizontal line. And today we're going to be a little more intentional about how we do this. We're going to identify a leading position, that guy right there, and we want to zero out everything below it. So to do that, we're going to take that row and we're going to multiply it by some row of the circled one, in this case, the first row. So to do that, we need to add 2 times the first row. So what happens if we do that? The first row will stay the same, and the second row becomes all zeros. So right here, we have a row of all zeros. So just like before in our original example, when we ended up with 0 equals 0, that indicated that we had infinitely many solutions. And this is going to be true in the case of systems of equations. When you end up with a row that's 0 equals 0, in most cases, that's going to indicate infinitely many solutions. We'll get to that in a second. We'll get to some other cases later. This is a strong indication there'll be infinitely many solutions. We're not going to be concerned about what those solutions look like, but this row right here is going to indicate there's infinitely many solutions. More precisely, we never able to get, we kind of missed the Y case. We never were able to pivot and do a row operations for keeping the Y column fixed. So that's really what's going to strongly indicate infinitely many solutions. Okay, we're not concerned with solving this explicitly. We're just concerned with how many solutions there are. Now, if we go back and change this equation back to the one where we know there's not many solutions, there are no solutions. Okay, we're going to change this one back to a 1. We're going to perform the same row operations that we did before. And the only difference is the arithmetic. So here we're still going to identify that one as our starting active pivot row. We want to zero out that one. And we're going to perform the same row operation. And what do we end up with? We're going to end up with the same row on top. And the bottom, we're going to end up with what will we end up with? We are going to end up with, we're going to end up with the same thing, except now we have a different row at the bottom. So this right here, if we translate what this actually means, this literally translated means 0x plus 0y equals 1, or 0 equals 1. So this is what we're going to call a bogus row. It's not a technical term, but at least it's very apt, it's very descriptive, that this is bogus. You can't ever have this. And if you have this, this means you're going to have no solutions. In much the same way that in our original example, when we had 5 equals 0, that was bogus and we ended up with no solutions. So whenever you end up with one of these rows at the bottom, it'll tell you how many solutions there are. Okay, so let's be a little more technical now. I want to just talk about and do an example about a kind of a standardized method. And kind of just do a bigger example and show you what the end goal is. So the goal here, I should mention, is to try to get the identity matrix. And the key emphasis on try. We'll be more specific on what's sufficient later, but you'll notice here, when we did this, we got our 1. We tried to get the identity matrix. We got our 1, we got our 0, but we couldn't get the 1 here. And because we couldn't get the 1 there, we couldn't get the 0 here. Right? And the same thing up before. We tried to get the identity matrix. We got as much as we could, but because the system didn't let us get the identity, we were stuck with this. But that tells us how many solutions there's going to be. So the goal here is to try to get the identity matrix. So let's do an example. We're going to have a 3x3 system, so this may take a little longer. So this first thing we want to do is we want to identify a pivot. And a pivot is a leftward non-zero entry. So in this case, we might identify this one. And we want to make that one as high as possible. So in this case, when we convert this to an augmented matrix, what we're going to do is this is our pivot position, but we want to make this one as high as possible. So we're going to exchange row 1 with row 2. And once we identify a pivot and put it as high as possible, we're going to try to zero out as many rows below it as we can. We can actually zero them all out if we do it correctly. But so that's our pivot. And now we're going to try to zero out all of these. All right, so now we're going to just do this all in one go. So this one, the second row is already a 0. We don't need to do anything there. But for the third one, we need to change it. So we're going to change row 3, and we're going to subtract 2 times row 1. Goes into row 3 to zero that guy out. So we get 2 minus 2, 2 minus 2, and minus 4 minus 2, and minus 4 minus 2 times 4. So altogether, what's going to happen? We simplify this and we'll end up with that guy. And so now keep in mind, this was our pivot right here, and we zeroed out everything below it. Those are now 0. And now the next step is identify the next pivot. So the key thing is we want to find the most leftward non-zero entry that's in a meaningful row. So this row is already done. That one's done. We don't need to worry about that one. So we're going to go to the next row or anything below it and find the leftward one. Now in this case, all of these are zeros. We can't pick those. Those are zeros already. So we're going to pick that one. And now we're going to zero out everything below that one. And once we're done with that, we'll do everything above. So once we identify the next pivot, we're going to zero out above and below. And we're kind of lucky here that these ended up being 1, but you should also scale them if necessary. All right, so now we need to zero out that minus 6. So we're going to take, what are we doing? We're going to take row 3 and we're going to add 6 times row 2. Put that into row 3. So this one's going to be 0, 0, minus 6 plus 6, minus 12 times 6 times 2. And you'll notice, okay, we wanted to zero out this. Those are the ones that we wanted to zero out from doing our pivots. And so now what do we want to do? This is now going to become 1, 1, 1, 0, 0, 1, 0, 0, 0, 4, 2, and 0. All right, so now we're almost done. Those were our pivots. These are the zeros below. And now we need to do this one. This is the one we need to do, the one above. So finally, we just need to take row 1 and subtract row 2 and put that into row 1. And at the end, we're going to get something that looks like this. So this is our kind of final form. Now this isn't the identity matrix by no stretch, but it has some important properties. It has the staircase pattern of leading ones. It has zeros below, above, and to the right of all the ones. Oh, sorry, zeros. This is important, zeros. And so this pattern here has a special name. We're going to call this pattern, which satisfies these conditions. This is called row reduced echelon form. It's just a fancy name to say an almost identity matrix. This is as best as you can do trying to solve some equations to get an identity matrix. And what's really nice about this is it's strongly indicative of how many solutions that you have. So if you're thinking ahead, you might notice, okay, that row right there, this one here just says 0 equals 0. That row right there just says 0 equals 0. So that's going to be indicative that there's infinitely many solutions, which is correct. But let's be a little more intentional about what this augmented matrix really says. This augmented matrix in reduced echelon form, if we translate it back to variables, says x plus y equals 2, z equals 2, and 0 equals 0. And so the key thing about what the row reduced echelon form does is it says which directions are defined, right? So what happened here, geometrically, what you can think about this is every time you're doing a pivot, you're saying in this particular case, this says that the x direction was principal. And so you can move, if you move in the x direction, you can eliminate all the others. And if you move in the z directions, you can eliminate all the others. But on the other hand, that the y direction, in some sense, is dependent on the others. Or conversely, once you define y, all the other ones are fixed. So if we go back to our equation, if I define y, because y was never a pivot variable, we never pivoted on y. If I choose a number for y, just for sake of argument, suppose I choose 2. I can now solve for x, and I can solve for z. So once I pick the non-pivot variables, it gives me all the other ones for free. And this leads us to some very nice rules. It tells us when there are going to be infinitely many solutions, no solutions, or a unique solution. So what is that? So if there's going to be a unique solution, that means that none of the variables are free and you pivoted on all of them. This is the same thing as a pivot for every column. This says that you can move in a unique way in each direction of each variable, and therefore you can invert it normally with a unique solution. For infinitely many solutions, you need two things. So one is you have to have this free choice or a missed pivot. For emphasis, a missed one can come at the end. So this one may be best put in quotes. It could be a variable later after you run out of space, but more importantly is that if you didn't pivot on one of the variables, that means you have a free choice. But more importantly, you also have to have no bogus rows. So you'll notice here that we didn't have a bogus row. If you had a bogus row, that means that automatically there'd be no solution. And it should go without saying, but for a unique solution, you also need no bogus rows. And finally, the no solutions, this is easy. This one is all about just having a bogus row. So this is kind of the rules on what you need to identify how many solutions the system has by just looking at its reduced form. So what we're doing is still the same. We're still applying row operations. You're still doing both things on the same side. We're still doing it in a systematic manner. The only difference that we're doing is instead of the aim being and the identity matrix, we may not be able to achieve that. We're going to do the row reduced echelon form. You can think of this is just a fancy name. I don't think it's important to remember the name. This just is the almost identity matrix. So keep in mind, if you're the identity matrix, the identity matrix satisfies all of these conditions. It has leading ones, it has a staircase pattern of ones, and it has zeros all below and above all those leading ones. So the identity matrix is like the perfect reduced echelon form. But if you can't get it, the next best thing is this thing called row reduced echelon form. And the row reduced echelon form strongly indicates which variables you have a choice with, and hence how many solutions you have. So for today, you're just expected just to do some row reduction on some different types of systems of equations and just identify how many solutions they have, whether they fall in the unique case, the infinite case, or the no solutions case. Next time, we're going to focus on how do you speak the language of the solution set when there are infinitely many solutions. If there's no solutions, you can just say no solution. If there's a unique solution, you just say that single point or that single vector. But if there's a unique solution, it's going to be a little hard to describe, but in fact, they're going to become a line or a plane or a hyperplane. And we'll learn how to do that next time.